Hi everyone, this video is on section 4.2, which is about selections and arrangements. Okay, we begin with something called the arrangement principle. And what it says is that the number of ways to form an ordered list of R distinct elements drawn from a set of N elements is this number. So Pn comma R. So here the letter P is short for the word permutation. So when we are arranging objects and we're counting those number of arrangements, we're going to call that count a permutation. Okay, so this Pn comma R, it's this product, n times n minus 1 down through n minus R plus 1. So I want to try and tell you a little bit about why this formula works. But first, I want to add something to the arrangement principle. So we're drawing objects from a set of n elements. And one thing that's being assumed here that I think should be stated is that these objects are being drawn without replacement. That means that once we've used one element from this set, we can't use it again. Okay, so let's see if we can derive the formula for this Pn comma R. So here you can imagine this as a problem where we have R slots to fill. And I'm going to fill these slots from my set that has n elements in it. So I might as well fill the leftmost slot first. I haven't done anything yet, so I have n choices to put in my leftmost slot. Now in the second slot, my number of choices is reduced by 1 because I have already chosen something for the first slot, and that something cannot be used again. Right, we're assuming this without replacement business. And so that leaves me with only n minus 1 choices there in my second slot. In the third slot, I can't use any object that I used in the first 2 slots, so that reduces my number of choices by 2. That means I've got n minus 2 choices in the second slot. And then finally, when we get to the final slot, we will have n minus R plus 1 choices. And then if I want to count the number of possible ways that I can do all of this, remember that's just the multiplicative counting principle. And so we multiply n by n minus 1 by n minus 2 down through n minus R plus 1, and that gives us this Pn comma R. Okay, now this formula can be expressed in terms of factorials. So I could write this as n factorial divided by n minus R factorial. Okay, here's a classic example of the arrangement principle in action. So we have a baseball team, and it has 24 people on the team, and we want to choose a batting order, right? So this would be a 9-person batting order from this set of 24 players, right? So in this case, our n is 24. And we're selecting an ordered list of 9 distinct elements drawn from this 24, right? It's ordered because we're looking for a batting order. We're not merely selecting players. We are choosing an arrangement, that is an order. And so all we need to do is replace n by 24 and R by 9 in this formula. So this would be 24 factorial divided by 24 minus 9 factorial. And as we see down here, this turns out to be this very, very large number of ways to choose a batting order from these 24 players. Okay, here's another example involving permutations. So the example is, how many different ways are there to rearrange the letters in the word gourmand? So we're trying to count, well, how many ways can we scramble those letters? Now, one thing that's nice about this example is that this word gourmand, there's no repeated letters, right? All the letters are different in that word. So we have 8 letters to choose from, and we're going to select 8 of those 8 and put them in some order, right? So in this case, n is equal to 8. That's the size of the set we're selecting from. And then r is also equal to 8. That's the size of the list that we're forming. And so what we form is P8, 8. Now they say that this is 8 factorial. Let's see if we believe that. Well, remember that P8, 8 is the first number, that is 8 factorial. And then we divide by 8 minus 8 factorial, right? So that's 8 factorial over 0 factorial. Now 0 factorial is not 0. 0 factorial is defined to be equal to 1. And so you do indeed just wind up with 8 factorial because 0 factorial is equal to 1. Okay, so anyway, there's 40,320 ways to rearrange the letters in the word gourmand. Okay, now another example, we have a kitchen drawer, and it's got 10 different plastic food containers and 10 different lids. But any lid will fit on any container. How many different ways are there to pair up containers with lids? So what you do is, you imagine you put the 10 containers down on the kitchen counter, and then it's just merely a matter of arranging the lids. Right, it's merely a matter of arranging the lids among those 10 containers. So I've got 10 lids that I'm selecting from, and I'm putting them in 10 slots. So the number is P1010, which, as we saw in the previous example, that's just 10 factorial. So it's about 3.6 million ways to arrange those lids. So in this example, we further investigate this issue of selection without replacement versus selection with replacement. So here we have an urn. So an urn is merely a jar, and it contains 10 numbered ping pong balls. So they're numbered 1 through 10. And now what we're going to do is we're going to draw 4 of these balls from the urn in sequence, and we're going to record the numbers on the balls that we select. So how many ways are there to do this if, first, the balls are replaced before the next one is drawn, and B, the balls are drawn and not replaced? So in case A, right, there's always 10 balls in the urn, so there are always 10 choices. And so this is just the multiplication principle that we had on the previous video, right? So if we have our 4 that we're drawing in sequence, right, we're going to have 10 choices here, and then whatever ball we've drawn there, we throw it back in the urn, and so there's still 10 there when we choose for the second. And again, we throw the ball back in the urn, so there will be 10 choices when we draw for the third and for the fourth. So multiplication principle says there are 10 to the fourth or 10,000 ways to do this. However, if we now go to part B is more of a selection problem, as we discussed a little bit earlier in this video, right? So we draw our first ball. There are 10 ways to do that, but that ball is not replaced. And so we now only have 9 balls left in the urn, And so we have 9 choices for the second. And then again, we have 8 choices for the third because we've not replaced either of the first 2 balls. And then there are 7 choices for the fourth. So there are going to be P10, 4, or 10 times 9 times 8 times 7, or 50,040 ways to draw the 4 balls under the scenario of part B. Okay, sometimes we would like to count the number of ways to select R elements from a set of N elements without considering the ordering of those R elements. So whenever we do that, and we want to make a count of such a thing, that's called the selection principle. And the number of ways to do that is denoted CNR. So C stands for the word combination. And you might notice that the number of ways to do that looks quite similar to the number of permutations of R elements from a set of N elements. In fact, if you look at this N factorial over N minus R factorial, that's the number of ordered lists of R elements drawn from a set of N elements. But now, to get just the selections without order, we divide our number of permutations by the number of possible orderings of those R elements that have been selected. Here's a classic example of a combination problem. So again, we have our 24-person baseball team. How many different ways are there to choose a group of 9 players? So we're not going to order them into a batting order. We're just going to choose 9 out of 24. So in this case, N would again be 24. And the number R that we're selecting is 9. And according to our formula, that's going to be 24 factorial divided by 15 factorial times 9 factorial. And it's this rather large number, about 1.3 million. But you might notice that that is much, much smaller than the number of 9-person batting orders that you could choose. So what I'm trying to say here is that this PNR is larger than CNR. Because in addition to counting the R objects you've selected, which is here, in PNR, you're counting the number of ways to order them. All right, now we have our urn again with our 10 ping pong balls numbered 1 through 10. And this time, instead of drawing 4 balls in sequence, what we do is we reach in and we grab or select 4 balls. So we don't care what order they're in. We just select them. And the question is, how many different ways can this be done? And so here, this is a classic combination or selection problem where we have N objects to select from, and we're selecting 4. We have 10 objects to select from, so N is 10. And we are selecting 4 of those objects, so R is 4. So we're told that C10-4 is 210 different possible combinations. So let's check that, right? So C10-4 is 10 factorial divided by 4 factorial times 6 factorial. So that would be 6 factorial divides into 10 factorial. That would be 10 times 9 times 8 times 7 divided by 4 factorial, which is 24. And now over here, 24 is 8 times 3, so this would be 10 times 3 times 7 left over on top after cancellation. And guess what? That's 210, just as was claimed here. Okay, here yet again is another selection problem. So here we have this sort of nonsensical word involving only 2 letters, and we want to count the number of ways we can rearrange the letters in that word. Now you might remember that we had this problem earlier about the word gourmand, where we wanted to count the number of rearrangements of those letters. So with gourmand, there were no repeats of letters. Here we have a ton of repeats, and you might notice the thing to observe is that once the P's are placed, right? So once we place all the P's in these 10 slots, then the F's have to go in the remaining slots. And so essentially all we have to do is choose or select 4 slots to put the P's in. And once we do that, everything else follows. And so the number of ways to rearrange this word involving P's and F's is going to be a selection of 4 locations from 10 locations. And you might remember from the last slide that this number is exactly 210. Now, if you read a little bit further down this slide, they're telling you that the answer is C106. And it turns out that C106 should also give you the right answer, because you might simply replace, or might simply select the locations to put the F's. So there are 6 F's, hence we would have to choose 6 locations. And luckily for us, C106 and C104 give us the very same number, namely 210. Okay, here's another example that we can do using selections or combinations. So we have this problem involving an equation, x1 plus x2 plus x3 plus x4 equals 13. We want to count the number of solutions there are if the numbers x1 through x5 must be non-negative integers. So here's one way to think of it. So we have our 13. So you can imagine 13 as being made up of 13 ones. Now, if I want values for x1, x2, x3, x4, and x5, what I can do is I can partition those ones into pieces or into groups. And in order to get 5 partitioned into 5 numbers, or into 5 groups, I need 4 little partitioning walls. So there's one there, there's another one, there's another one, there's another one. So in all, I've sort of got 17 slots. Some of the slots have 1s in them, and some of the slots have these partitioning walls in them. So I've got 17 slots total, and what I want to do to get a solution is choose 4 of those locations to put partitioning slots in. And that number, C17,4, is 2380. So that's the number of ways you can make a solution, or choose a solution to the equation. So now in the partition that's shown here, what's the solution? Well, here x1 is equal to 4, because there are 4 1s there. Now here we have 2 partitioning walls immediately next to each other. So that means that x2 is 0. x3 will be 1, 2, 3, 4, 5. x4 is just 1. And x5 is going to be 3. And one way that combinations come up in algebra is through what's called the binomial theorem. So you might remember in algebra multiplying polynomials and how difficult that can be. Like, for instance, if we took 3x minus 5, this binomial 3x minus 5, and we raise that to the fourth power, that means you got to take 3x minus 5 times itself 4 times. And remember, you've got to sort of multiply them incrementally and account for middle terms and all this other stuff. And it becomes just a very, very nasty calculation. Ultimately, you wind up with, this polynomial, which is 3x minus 5 to the fourth power. Now, luckily, there's an easier way to do all of that, right? So the theorem is if you let j and k be non-negative integers such that j plus k is equal to n, then the coefficient of the a to the j times b to the k term in the expansion of a plus b to the n is this combination Cn comma j. Right, so in other words, we have the binomial theorem, which says this, that if you want to raise this to the nth power, and you're looking for the coefficients of all these terms, then they are given by these binomial coefficients here, where here I should tell you that when you see n atop j like that, that is another notation for Cn comma j. Right, so the point is that when you're multiplying, taking a power of a binomial, there's a formula for producing it that doesn't require you to do all of this FOIL and computing middle terms and stuff like that. All right, so for instance, let's go back to this problem of computing 3x minus 5 to the fourth power. Right, so we can do this using the binomial theorem. So in this instance, a will be 3x, and b will be minus 5. So when we apply this binomial theorem, we wind up with this expansion, right, where whenever you see like 4 atop 1, 4 atop 2, that's means C41. This means C42, etc. So you just compute those numbers according to our formula for combinations, and you get 4 choose 1 is 4, 4 choose 2 is 6, etc. And then you wind up with this same polynomial that we found on a previous slide after a lot more work.